course on calculus differentiation. In the previous lecture, we have seen theorems related to monotonically increasing decreasing functions with the help of the derivatives, and we have seen the continuity of the derivatives. We forgot to make some remarks for this theorem. That is the first one that I have told when I was explaining the statement of the theorem itself. That is, this theorem is true even if you take the reverse inequality. That is, f of f prime of b is smaller than the f prime of a. Even if you take that way, this theorem holds good, right? And if a function is differentiable, then its derivative may have discontinuities of second kind, right? It will not have discontinuities of other kind. These are the two remarks that we would have to make at the end of the continuity of derivatives. The talk of this theorem relies on the L'Hopital's rule. Yes, we all might have studied the L'Hopital's rule and worked out few problems based on this L'Hopital's rule. But what does this L'Hopital's rule actually tells us? Let us get into those details in this lecture. Here we have two differentiable real valued functions in a particular interval AB. Okay, right, these are the things that we have, and this function is, the derivative is not vanishing at any points. That is derivative of g, that is the denominator that we have. Okay, and this a and b can be what? It can be anything in the extended real plane with only one condition, that a has to be smaller than b. A can be equal to minus infinity and b can be equal to plus infinity. Okay, and along with these things, we further assume, or we further suppose, that f prime of x upon g prime of x goes to some limit a as x approaches a. Okay, with these things we have the following things. And if we take f of x and g of x approaches to 0 as x approaches a, either this happens or this g of x approaches to plus infinity as x approaches a. Either of this happens. Whatever happens, this limit is going to approach a as x approaches a. This is what we will have to prove in this theorem. Let us get into the technical details of the proof. Here, the basic assumption, this one, this is what we take it as equation 1, right? So with that, what should we prove? We will have to prove these things. Okay, let us go step by step. First, let us consider the case when this limit a in this way. It can be either minus infinity but never infinity, plus infinity. Okay, with this we choose some. Okay, let us consider this as a real line. Okay, only this point cannot be chosen. You can choose anywhere else your a. Even if you choose your a here or a here, you can always find out some quantity which is between a and infinity. That is what we take it as q. Okay, your q somewhere lies here, and then we choose some r that lie between a and q. So we have chosen some entries of this form from our assumption. What is the assumption that we made? In equation 1, what we have, that is f prime of x and upon g prime of x goes to a as x approaches a. With these things, what we have, this, since this approaches a, sorry, I think I must leave this as it is, minus infinity, plus infinity, a may be anywhere, we choose some q between. Okay, this is the case. Even if you choose your a here, you can always find out q and r of this sorts, right? Okay, we have chosen some r where x lie between a and c. C is some, okay, supposing this is my a and this is my b. Okay, I think I have to do it in other thing. This is my a and this is my b. In between I choose some c. Okay, how can we plot these things? If you wish to plot these things, the choice of A and Q, sorry, the A choice of A and B lies in the x-axis and choice of these things lies in the y-axis. Okay, we are not writing it completely, we are specifying in a separate things. Okay, this is how we have chosen A. Then between A and C, sorry, between A and C we choose two other points, namely x and y. So with the help of this x and y, we make use of the generalized mean value theorem for this x and y. We choose some random points between A and C, and to those points we apply generalized mean value theorem, right? And here we will have some dummy variable, and that has to be chosen between x and y. Okay, with this what we have. So if you see here, we are taking this to this side and this to this side, this to this side. So once we do so, what we get is this quantity, right? And we wish to write f of x in the x terms in the first place, and that is why we get like this. And this quantity is also less than r, and we take this to be equation 4. After this, we are assuming the condition 2. What is the condition? That is, f of x and g of x approach 0 as x approaches a. Then from 4 what we get is that this quantity and this quantity goes to 0. So you will be left with minus f of y upon minus g of y, which is same as that of f prime of t upon g prime of t, which is less than r. This is what we have. This minus and minus gets cancelled out, and we are left with this quantity. Sorry, we are left with this quantity. So with this, what shall we conclude? As this f of y upon g of y smaller than or equals r, which is smaller than q for some y between a and c, because we have chosen a, b here, x, y here. In between we have chosen some t. Okay, actually we have c, which is between these things. Sorry. Yeah, this is what we have done, right? So between a and c we have some y such that this things happened. So that is what we have written. And suppose, so if 2 holes, we are done. Suppose 3 holes, that is g of x goes to plus infinity. If this happens, what happening? We'll keep y in this. Okay, we'll keep y fixed, and we choose some point between a and y such that these things happen. G of x is bigger than g of y, and g of x is positive. If you see, here is your a, here is your c, here is your y. We fix this y, and we have to choose some x between these points. In between we can choose any x such that it has to satisfy these conditions. We are choosing a point which is chosen in a way that it satisfies these conditions. We are choosing that way, right? So once we choose that way, what we are going to have? We will have, okay, after choosing such points, we are multiplying a quantity, that is the denominator. Take the denominator as it is, g of x minus g of y upon g of y. Sorry, g of x, I suppose. So we are multiplying this quantity with this. So when we multiply it with both the sides, what are we going to get? This is the left hand side and this is the right hand side. We know that this quantity is less than r. So we get this. Okay. Now we just this quantity and this quantity gets cancelled, and here we are splitting these things up. Okay, g of x upon g of x minus g of y upon g of x. We write this way and we get this. And here also we may do the same, that is f of x upon g of x minus f of y upon g of x, and take this to this side, so you get this quantity. At this is g of x gets cancelled, so you will have r times of 1 minus this thing. So r minus r times of this quantity. This is happening for some x in a and x between a and c. And in this case, let us take the limit as x approaches a. As x approaches a, what we have by 3. This 3 tells you that your g of x goes to plus infinity. So when your g of x goes to plus infinity, this quantity vanish and this quantity vanish. We will be left with what? F of x upon g of x is less than r. We write this as less than or equals r, which is less than q, as x approaches a for some x between a and c. Right? So we are combining 5 and 6. Whatever happens, whether we assume 2 or we assume 3, finally we landed with f of x upon g of x less than q for some point between this thing. Actually we had a here, c here, in between we choose x and y. This between these two things we choose some c2, that can be anywhere, okay, such that these things happen. Now we have done for the case minus infinity less than or equals a less than plus infinity. But when you choose this case, what is going to happen? And in this case we are choosing some point P, that is, let me draw and tell you. Okay, I'll have to do it in another color. So suppose we have such thing, this is our plus infinity and this is our minus infinity. Our P may be, sorry, our A may be anything, that may be even here or even here, okay. We shall choose A anywhere here, and we'll have to choose some P between A and minus infinity, and the rest follows as we have done in the previous things, right? So this is going to happen. Combining these two things, we can squeeze our f of x upon g of x between this p and q values for some x in a and b. Okay, here we had a, so between a and b we were talking. Here we have come this way, and when we go very near to a, what is going to happen is that this p will come near to a and this q will also have to come near to a. So finally what we can conclude, as x approaches a, we get this quantity to approach a, and this completes the proof. Thank you.